In this lecture, we are going to discuss on another topic of interest, that is pumps and turbines. This is another class of machinery one will come across in major chemical process plants, steel plants, power plants, ships, aircrafts. So, we have to see how we can find out the major faults in such pumps and turbines through vibration signature analysis, through motor current signature analysis, maybe at some times through wear debris analysis as well, and many times of course, NDT inspections are done on such critical machine components like aircraft turbines and so on. So, I will classify these pumps and turbines based not on the principle of their operation, but rather on the type of fluid they pump, type of fluid they use. Okay. As you know, pump is a mechanical device where when we give in some sort of an energy in the form of an external energy to give certain output energy to the pump in terms of pressurizing the fluid, so that it can gain much potential. So, the pump capacity, the power of the pump, gamma q h, okay, wherein gamma is nothing but rho g, q is the discharge rate and h is the height through which this fluid is to be pumped up. Okay. And this is a requirement, because I need to develop a certain pressure head in a pump, okay, because it can flow. A pressure head is required in the pump. So, these pumps are usually driven by a motor through a coupling, and then we have the pump. So, this pump can again be positive displacement or could be dynamic. So, in dynamic they could be axial, they could be centrifugal, and so on. And the most common pump which you will see is the centrifugal pump, and many of you would have seen this centrifugal pump used for pumping water in the fields. They produce a certain water at a particular flow rate and a pressure, so that we can irrigate the lands. Lot of chemical process plants, if you talk about a distillery, refinery, there are a lot of pumps. Okay. Imagine the pumps which we were putting it under the ground, okay, to pump out crude oil from the bed of the ocean, okay, underneath the bed of the ocean, crude oil pumping, pumping of water, domestic supplies, pumping of water, firefighting, etc., chemicals in refineries. So, they all require pumps, and these pumps have to be powered. Another pump is the pumps which are submerged in liquid, the sewage pump inside pipelines, large pipelines wherein we have axial flow pumps, okay, pumping of crude oil, etc. So, these pumps can have defects, okay, and then how do we rectify them? Another important application is in nuclear plants. Think of a nuclear plant. Okay. Think of a nuclear plant. How do I monitor the health of such machines or such pumps? So, the candidates, this is what we are going to focus on, the nuclear plants and then submersible pumps, I will pose a challenge to everybody right now. The fact that we have studied about vibration monitoring in details in this course. Okay. But can they be applied in nuclear plants and submersible pumps? Because to install a transducer, I cannot go inside a nuclear plant. I cannot go underground and mount a transducer in a submersible pump. So, these are issues, okay, and we will see how this can be done. The pump diagnosis in a nuclear plant and submersible pumps. Another important machinery which we will study in this course are turbines. Usually turbines, again by the type of fluid, will have two types. One is the steam turbine, which is there in almost all the land based power plants, thermal power plants in our country. Of course, we have the hydel power plants, where we have hydro turbines like the Kaplan or the Francis turbine, or even sometimes the Pelton wheels. So, we will briefly talk about the hydraulic turbines as well, and then of course, the gas turbines in aircrafts. Gas turbines are used to power naval vessels, and even sometimes small gas turbines of 20 megawatt capacity are used in captive power plants in many industries run by gas turbines for generating electrical power. So, wherever the turbines are used to excuse me, turbines are used to generate power, what happens? The turbines rotate and they are coupled to an electric generator. And if you talk about large power plants, steam power plants, 200 megawatt or 400 megawatt super thermal power plants, etc., they generate, they have turbines running on steams, and these turbines rotate and the rotor of the electric generator, and then an AC current is produced. By the way, I should tell you, when we talk about the frequency of the current which is being generated in our country, this is this time period corresponds to 1 by 50 seconds, because our supply is 50 hertz. So, the speed of the rotation of the rotor of the electric generator is governed by the turbine. So, there are a lot of control mechanisms as to, so that I do not produce a current supply frequency less than 50 hertz or greater than 50 hertz. So, I have to produce the electrical supply frequency F supply at 50 hertz, and that is my primary requirement of a power plant, okay, with of course, continuously and so on. But these turbines, when you are talking about 200 or 400 megawatts, they are very, very large in size, and these rotors are so heavy that they are supported on hydrodynamic bearings. Hydrodynamic bearings. Okay, and there are a lot of mechanisms so that we operate them at stable frequencies. By frequencies I mean rotating speed, and so if I give in more steam, it is going to rotate at high speeds, but then this has to be governed. So, I will not go into the controlling mechanism of such such power plants, but it is pretty complicated. We have discussed about the individual machine components like rotating shafts on bearings, shafts carrying gears, shafts carrying pulley, shaft having misalignment. But when I talk about a turbine or a pump, okay, maybe how do we monitor the conditions of a turbine? So, this is not a single component. So, if you think of a turbine, let's talk about the turbine first, and then maybe I will come to the pump later. So, in a turbine, what are the important characteristics? Large rotor supported on journal bearings. Okay. And usually all the phenomena, of course, in the turbine there could be blade vibrations, there could be blade problems, there could be casing problem, casing defects. Because of high heat there could be creep, etc. There could be seal problem, because we would not like the seals to leak, and so that the steams pass out through the shafts. So, in fact, these seals are mounted something like this as a rotating component, okay, which is tightly, and the seals are actually given here. They are spring loaded, and then you can have another component here. Okay. And this is the shaft, which can be, which will be having the shaft could be rotating, it can be carrying compressor sets and so on. And of course, as I was telling you right in the beginning, if I go back here to this figure here. So, turbine, the first place would be of course to put vibration signals at all locations. By all locations, what do I mean? Of course, all the bearing locations, all the foundation locations. Okay. These are all the locations where you can mount transducers and so on. But the problem in nuclear plant is that this is not accessible. The problem in submersible pump is that pump is not accessible. So, that is something we will discuss later on. And the normal method of vibration signal monitoring is well understood by now. So, whenever we have a machine, we just install the transducers and find out the characteristics. First of all, in the time domain itself, based on the ISO standards, we see whether the levels are within the allowable limits as per the standards, as per the power of the machine. That is number one. And if we want to diagnose faults in the turbine, what we do through vibration monitoring is install the sensors at all the bearing locations or the foundation locations, and then do a signature analysis to find out unbalance, misalignment, gear defects, blade missing blade, etc. The techniques of FFT, substem analysis and null-up detection can be used. That is good enough. But I was telling you for the case when this turbine itself is not accessible. So, for example, a nuclear plant. So, how is the health monitoring in turbines in nuclear plant done? First of all, because of high radioactivity, we are not allowed to go inside the plant. So, they are permanently installed sensors. By sensors, I mean usually in such turbines at the journal bearing end, usual practice is to put some sort of an non-contacting type eddy current probe at, this is actually at 45 degrees. X, y, and you can do a lot of orbit analysis to defect, and we have discussed about orbits in one of our earlier classes to find out the defects in the. But these sensors can be eddy current, can also be vibration transducers like accelerometers. The question is, suppose a nuclear plant is made and you are not supposed to go inside it, and it has a life of about 20 years. So, what do we do? They put a lot of extra transducers, extra or redundant transducers are installed, suppose, and then all you have is because if you go to a nuclear plant, they are actually in a containment building, okay, and then all the machines are there. So, all you can have is these sensors signals coming out from such a plant. And then you can do the analysis, vibration analysis. But another important technique of finding out faults in turbines is through what is known as motor current signature analysis. And this is very helpful for fault detection in submersible pump, and then in even in gas turbines. I will give you an example. I mean, I believe we have talked about motor current signature analysis in submersible pumps for the fact that in a submersible pump which is under the ground, which is rotated by a motor, and then all we require is an Hall effect current sensor, and then we can have an A-to-D process, and then we can have an signature analysis. And this could be under the ground, so we need not worry about. The same is true for turbines. In fact, if you think of the marine propulsion system, they have what is known as the gas turbine generator. So, the turbine, which is the gas turbine, is driving a generator, and this generator is actually used to power devices in the ship. And this is the generator, and this is the coupling. So, I will show you a few pictures of we did condition monitoring on a gas turbine. This is the gas turbine, and this is coupled to a generator. Okay. I am sorry, this is the gas turbine end here. Okay, you can see the heavy exhaust here, and this is the generator. And if you will see here, we have put a accelerometer on the bearing housing of the generator, and this was required so that we can, and this was a case study which we are doing for the from one of our sponsored projects by the DRDO for the Indian Navy, wherein we are trying to see the feasibility of using motor current signature analysis for monitoring the health of a gas turbine. This is a small gas turbine in a test establishment. This is a replica of the actual gas turbine. This is one of the actual gas turbines which is used in an marine propulsion unit, and we have put an accelerometer here, a charge type accelerometer here, to measure the vibration, so that we would like to see whether the defect characteristics of the generator vibration can be picked up by such a transducer. Okay. And then I will come to the associated problem. This is another view of this, wherein we are monitoring the accelerometer by an acceleration by an uniaxial vibration monitoring. This is another view of, and it is pretty noisy. So, that we have put in earmuffs here. It is a very noisy test environment, and you will see these are the chutes for the exhaust of the gas turbine. Okay, because this is a stationary unit, otherwise this would have been normally used to power the the ship, but then we have only coupled it to drive the generator, because for own generation of power in the ships, they have what is known as the gas turbine generators. Okay. So, the small gas turbines have high power to weight ratio, and they are very convenient in ships, and this was being used to drive a generator. Okay. Now, what happens is another view in the naval establishment is we measured, because this generator was delivering power, okay, to a resistance bag. Whatever we generated power here, it went to a electrical load. This is a dissipative load and by resistances. So, onto this we put a Hall effect sensor, okay, and this is the Tektronix Hall effect sensors put on one of the phases of the load, output load, and then we can correlate what is the defect in the generator and then in the turbine, because the principal idea behind MCSA is the current gets modulated by a load torque. Okay. So, in the case of a motor, driving a mechanical unit, if this mechanical unit has a defect, it is going to load the motor and then the motor current drawn will be loaded up. But same is true here. If the like we had done in the case of a in the laboratory, I had shown you earlier that we had a motor driving a gearbox which was incoupled driving a generator okay, and then there is a load. Okay. So, we had established that if there is a defect in the gearbox, motor currents get modulated, then we have measured it this way through an Hall effect sensor. Okay, we have demonstrated this earlier. Now, the other way also happens if there is a load defect in the gearbox, the generator voltage which is generated by the generator will have ripples this is the time generator voltage, and these ripples are at a frequency at the defect frequency. Of the mechanical unit, and that is the turbine in our case. In fact, this is a powerful technique that any rotating machines, I just showed you for the case of a turbine. So, any rotating mechanical device, if it is coupled with an generator, the ripple frequencies are characteristics of the defect in the mechanical device. So, this is one of the important observations, and in fact, our group at IIT Kharagpur has a patent on the same, for the fact that any mechanical rotating device which is powering a generator is going to generate a voltage, and this voltage will not be clean. Voltage will have ripples. So, if somebody can understand and measure, capture these ripples and understand the frequencies, we will see that they will are characteristics of the defect in the mechanical device. So, this becomes a very powerful technique to find out defects in gas turbines, powering aircrafts, powering marine systems. So, these are very powerful technique. Okay. This is one of the examples of the view of one of the gas turbines, which is used for the marine propulsion system. This the compressor, the low pressure compressor on the front of the gas turbine. This red cover is just a cover, because this has just come to the bay, and this is in one of the naval establishment units where we are doing measurements for our project. And this has a low pressure compressor, a high pressure compressor, the combustor, and then the series of turbines, and each one of them has sets of blades. Okay. And so, how do you do the health monitoring of such gas turbines? Okay. So, the best place would be to keep vibration transducers along these rings. Okay. You will see a lot of these rings and braces are there, because you obviously cannot access them. The challenges, instrumentation challenges for monitoring gas turbines are such. Because of high temperature, and those of you we had studied that we mount accelerometers using magnets, but these magnets are very soft and they lose their properties. In fact, they crack. In fact, I myself have lost a lot of magnets mounting accelerometers at locations which were at high temperature. I realized later on, once I had the cracked magnets. So, they have to be withstand the high temperatures, and nowadays we have transducers which can go up to 600 degrees Celsius, accelerometers, piezoelectric accelerometers. And they can be mounted permanently also, but again the problem here is, these temperatures could be even higher than 600 degrees Celsius. So, certain, that is one issue, the temperature, and then the itself is how do you lay the cables, and the location becomes a problem. Okay. Because I cannot be close to the bearings, because if you look at the these shafts, okay, these bearings are somewhere close. So, bearings are not accessible. Bearings are easily not accessible from outside. So, this is again a challenge, and as you know, in all these machines the vibration reflects pretty well at the bearing locations, and if I cannot access the bearings, how do I measure them? Okay. So, to some of the, and that is why MCSA has become a good candidate. Next is, we can use a lot of the NDT techniques. Of course, NDT techniques cannot be real time, but it is a good practice, particularly for gas turbines or turbines. We can do on quick ultrasonic inspection. The internals of the turbines can be looked through visual inspection, boroscoping. Okay. And of course, another technique people nowadays are used are on laser based measurements. and the optical rotary encoders for what is known as detecting the instantaneous angular speed. These techniques are over the conventional vibration analysis. We will study about MCSA and NDT in the later classes, but these are techniques wherein this can be used to measure and understand more about such gas turbines. But there are few other associated problems, like in such turbines, be it the particularly in hydraulic turbines, there is a limit to the maximum flow rate. Okay. Because if the flow rate increases and the velocities become so high, because to conserve energy, the pressures of the liquid, if they fall below the vapor pressure, so what is going to happen is this vapors will be formed or bubbles will be formed in the pipeline. Inside the suction pipe. Okay. And when this bubbles come up with time, come up to the surface to air pockets, they will burst. So, they are like hammers, high frequency hammer, and this is what is known as the cavitation. So, cavitations limits the operational pressure or flow rate of turbines, and there has to be, and this cavitation goes undetected. It is as if the inner walls will get pitting will be there, and this bubbles, because when they burst they will release energy and as if they are hitting, and if this goes unnoticed, they will weaken the structure, and then lot of the surface will become weak, it may eventually break. So, to monitor cavitations, because they are high frequency, we can always have the high frequency. It could be vibration monitoring. Nowadays, underwater piezoelectric accelerometers are available. Okay. But the most important thing, and this can be put on the pipeline, and the most important is the cable, the triboelectric low noise triboelectric cable, and they have to be watertight with good silicone sealant. Sometimes these cables are more costlier than the piezoelectric accelerometers. Okay. So, we can monitor the vibration of because of cavitation on the pipeline, because if this goes unnoticed, they will damage, they will pit the internals of the pipeline or the casing, and then they will become weak and they will maybe start to leak and then damage. Another important aspect which will go is the leakage. So, leakage has to be provided with seals, good seals. I think I need more papers. Okay. So, this many things happen in chemical plants. In the pump impeller, if I have just draw the blades, there could be particles which will get stuck, sometimes not uniformly. So, these are particles which will get deposited. Okay. Because of this deposited particles, there will be unbalance. Okay. And this unbalance will again get detected at the bearing locations. So, if I have a shaft and then either there can be unbalance and there can be because of pitting. So, all these will give rise to again the same problem which you see in the frequency in the vibration signal, a strong 1x component. So, this can be one will lead to the other, and many times again in process plants they go for visual inspection, and there are a lot of, particularly in process plant, a lot of sight windows, glass, very high pressure quartz glass sight windows are provided in such equipment to visually see from the outside what is the condition goes. And associated with these impellers getting defected, bearings there will be load on the bearing and then misalignment. So, eventually again they will rub on the casing. This rub I told you in the case of the pumps is also severe in the case of turbines, particularly gas turbines. Okay. And then this will again give rise to a lot of problem, and we discussed in a few of the classes earlier how this rubs can be detected by what is known as the non-stationary signal analysis. Like wavelets or FFT. Okay. And particularly associated not with hydraulic turbines, but with steam turbines and gas turbines, a serious problem is the bearing temperature, and there are lot of control measure circuits available. So, that the gas turbine the bearing temperatures are below the rated temperature of usually 75 degrees Celsius. And many of you, those who would have gone to power plant, there are certain very important parameters which are monitored, and one of them obviously is the generator output speed, because that output speed would correspond to the frequency of electrical power generation, and that has to be strictly at the synchronous speed of 50 hertz. And you know the effect, if the speed falls below that, there are a lot of circuits, a lot of protection circuits in equipment which will shut them off if the supply frequency is less than 50 hertz, because of the fact that many devices are synchronously, many timing circuits are dependent on that supply frequency, and so your machine would go haywire if these frequencies were less than the tolerated levels. Okay. And you would have heard of the grid failure, because suddenly the machine shut down automatically, the loads would again decrease, and again that would lead to again high speed increase. So, there will be a lot of frequency fluctuations. So, that is one of the hunting of the machines, and that has to be avoided. Okay. And because of this speed fluctuation, because of the change in frequencies, there will be a lot of torsional vibration associated. Torsional vibrations due to change in supply frequencies. Because the speed is changing. Speed is changing. Okay. And I have seen many times, particularly crankshafts of large machines, structures failing because of such speed fluctuations. So, many times in many plants, input power frequency, at least in India, has to be maintained constant and 50 hertz, because of the load, poor power generation. Sometimes this fall, but then again if they decrease, so this will give rise to speed fluctuations, and these speed fluctuations will introduce fatigue torque, torsional loads, and lead to premature shaft failure. So, in a power plant, parameters monitored in a power plant from a machinery health point of view is of course the power generation frequency, then the turbine rotational speed, bearing vibration, bearing temperature, of course, the steam consumption rate, okay, and of course, the voltage etcetera is there, but these are the parameters which are to be monitored, so that we will know whether the turbine is stable or not, and so on. So, in conclusion, pumps and turbines are important machineries which are there in all power plants, in all nuclear power plants. Gas turbines per se are used for marine propulsion, for captive small power plants, for aircraft propulsion. So, they have their online condition mounting techniques by vibration. Motor current signature analysis is another new candidate which can be used for analyzing and monitoring such systems. Of course, bearing temperature can be monitored as well, and particularly for gas turbines which are used in aircrafts, lot of NDT inspections are done in the maintenance workshop, lot of on-site internal inspection through techniques of visual inspection using boroscopes etcetera are done. Some of the NDT techniques we will discuss in the next few classes down the road, and all including MCSA, but this was just to introduce you. There are techniques of other than vibration monitoring like motor current signature analysis and NDT techniques which can be used to find out defects in machinery. Okay. Thank you.